for USACO's 2021 December contest at the bronze level. Problem number 1, lonely photo. Farmer John has recently acquired N new cows, where N is between 3 and 5 times 10 to the 5th, each of whose breed is either Guernsey or a Holstein. I point this out in every video when I see it. 10 to the 5th is a sign that you cannot do an N squared algorithm. We will talk about that in a minute. The cows are currently standing in a line, and Farmer John wants to take a photo of every sequence of 3 or more consecutive cows. Okay, so have to have 3 cows, A, B, and C, or more. However, he doesn't want to take a photo in which there is exactly 1 cow whose breed is Guernsey, or exactly 1 cow whose breed is Holstein. He reckons this singular cow would feel isolated and self-conscious. Okay, so basically what that means is if we have like 1 Holstein only with Guernseys, or 1 Guernsey only with Holsteins, that's not going to be valid photos. We don't want to take those photos. After taking photo of every sequence of 3 or more cows, so he's taken every possible photo that could exist, he throws out all of these lonely photos in which there's exactly 1 Guernsey or exactly 1 Holstein. So basically what you're looking to do is for every single combination, every single possible combination where the cows are in a line, every single, I guess, subset of the cows, anytime there's only 1 G or 1 H, we want to discard that photo. Given the lineup of cows, please help Farmer John determine how many lonely photos he will throw out. 2 photos are different if they start or end at different cows in the lineup. Input format arrives from terminal standard in, which is just being typed into the console with standard input. So just somebody's going to type and hit enter. The first line of input contains N, which is how many cows there are. Second line contains a string of N characters where the ith character is G if the ith cow in the line is a Guernsey. Otherwise, it will be an H and the ith cow is a Holstein. So basically, it's just the lineup of cows. GH, GH, GH means we go Guernsey, Holstein, Guernsey, Holstein, Guernsey, Holstein in that order. Output format printed to the terminal standard out. That's just a C out or a system out print line or whatever. Please print the number of photos Farmer John will throw out because they're lonely. Okay, so any photo where there is only 1 G or only 1 H. Sample input is 5, and then sample is GH, GH, GH. The number of photos thrown out was 3. Those photos specifically were the GHG, the HGH, and the other GHG. That's 3 photos where there was only 1 H in the first one, only 1 G in the second one, and only 1 H in the third one. Sample outputs 3. Every substring of a length 3 in this example contains exactly 1 cow whose breed is Guernsey, exactly 1 cow whose breed is Holstein. So the substrings represent lonely photos would be thrown out by Farmer John. All longer substrings, GHGH, HGHG, and the whole thing are acceptable to him. Scoring, cases 2 through 4 have N less than 50, cases 5 through 10 have N less than 5,000. You can get through the first 10 test cases with an N squared algorithm. 5,000 is small enough to do that. But you can't get through it with an N cubed algorithm. So let's talk a little bit about this time complexity. If you have a sequence of cows, for example, if I have H, and then G, G, G. By the way, if you haven't done this already with paper and pencil, I recommend getting paper pencil, try out a couple different combinations. This one, anytime you have output where it looks like the sample input is really specific, like this one is specifically alternating, it's good to try some variations on that where it doesn't follow that pattern. So the example I'm going to use is H and then a couple G's and then H. We're going to do 4 G's and then 1 more H. Okay, so N squared algorithms briefly. The way an N squared algorithm works is if you are in a situation where you have to compare everything to every other thing or test every possible combination, you're in N squared. So for example, let's say like I had to compare this cow to that cow. And then I had to compare that first cow to the second cow. And then I had to compare the first cow to the third cow. And I had to do that all the way down. And then I moved to the second cow and I compare the second cow to the third cow, and then to the fourth cow and so forth. That's an N squared algorithm. And the reason why is because for every 1 cow, the amount of work you have to do is N, because N is how many cows there are. So if we've got 10 cows, 1 cow has to look at 10 cows. And every cow has to look at 10 cows. So for each of N cows, I have to do N operations. That's N times N, which is N squared. And that's what we mean when we're talking about N squared. Now, if I wanted to look at and consider every single possible subset, for example, from here to here, it's got to be 3 at least. From here to here, from here to here, from here to here, from here to here, for each one of those with this one as the starting point and trying every possible ending point, I will have roughly n photos where H is the first one. Then from this G, here, 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 and so forth. Now that's already n squared. But if I have to look at this subset here to here, and then find out how many G's and how many H's there are, I need a loop to go through each of those. So for every possible pair, I now need to run through all of them. That's yet another n, which is n cubed. N cubed with, what did they say the limit was? 500, I think. Look at that. 5,000. Okay, so 5,000 cubed is, how many zeros is that? That's big. 1, 2, 3, 1, 2, 3, 1, 2, 3. That's 1.25 times 10 to the 9, 10 to the 11th. Anything above 10 to the, about 10 to the 9th is too big. 10 to the 11th is going to be way too big. So if we have to create our subset and then go through and check every single cow for every single subset of cows, let me put that back. H, G, 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 H, G, 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 H. If for every single cow, we have to consider every single other cow as a potential stopping point, and then for that subset, for every subset, we have to run through and count all the cows, we're going to go way over our time complexity. Now, if you happen to have already studied a little bit of silver, you might think that a prefix sum is a good solution for this, because a prefix sum will allow you to very quickly look at how much of something is in a specific subset. I'll give you a quick introduction to that, but we're not going to use that to solve the problem. The way a prefix sum would work in this case is you would have a counter that starts at 0. And every time you hit an H, you'll add 1 to it. So here's an H that goes up to 1. There's a G, still 1. There's a G, there's still 1. There's a G, there's still 1. Here's an H that brings us up to 2. This is a really important technique for silver. This comes up a lot in silver. 2, 2, 2, 2, and 3. So basically, every time we hit an H, we add 1. Now, what that means is that, for example, considering this H, after this H, I had a value of 2. And before this H, I had a value of 1 because the presence of the H caused that to go up by 1. But what that means is that I can pick any arbitrary starting point and any arbitrary stopping point, and I know how many H's there are because I know that after this G, there are 2 of them, and before this G, there are 1 of them, which means somewhere in there, and I don't care where, there must be an H. And you can do that for any subset. If I go from here to the very beginning, then I've acquired 2 because I went from 0 to 2. But if I were to start at the third value from here to here, then I've only acquired 1 because it's 2 minus 1. Now we don't have to, and then you would do that also for the Guernseys. Let me go ahead and do Guernseys real quick, just since we're already come this far. So at the very beginning, we have 0 Guernseys. After the H, we still have 0 Guernseys. Then we've got 1, 2, 3 of them. Then still 3, 4, 5, 6, 7, and then still 7. So if I want to know how many Guernseys there are, let's say like I'm going to pick a set here. If I go from here to here, G, G, H, G, 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 then I know that after that G, I had 6 Guernseys. And before that G, I had 1 Guernsey, which means I acquired 5. And I know that after this Guernsey, I had 2. And before that, I had 2 Holsteins and 1 Holstein, which means I went from 1 to 2 Holsteins, and I went from 1 to 6 Guernseys, which means I picked up 5 Guernseys and 1 Holstein. Now, potentially you could use this, but again, this is an n squared algorithm. This will get you through, I think, through all these test cases, but it won't get through test case 11. Test case 11 actually goes up to that 10 to the 5th. Now, there is essentially a linear algorithm for this as well, and it's easier than using the prefix sums. It's a little bit more of a straightforward solution, I believe, and it doesn't rely on the prefix sum, which again is sort of silver level knowledge. So let's focus on the simpler way to solve this. Essentially, what you need to do is for every single cow, we are going to send a runner out until we either hit the beginning of the string or another H. And then we're going to send a runner out this way till we again hit either another H or the end of the string. While we're doing that, we just want to count how many G's there are on the left, how many G's there are on the right. Once you know how many are on the left and how many are on the right, in this case, so this is just a while loop. So essentially what you would do is start a runner, left-hand side runner on this value right here. And while it is different than this cow, keep subtracting 1 from its index until, again, you either hit the beginning or whatever. As you do that, count how many G's you have. I counted 3 G's here. Send another runner out this way. And while it is different than the H, for example, keep sending it forward until you get to the next H. And that'll establish you as having 4 G's here. Now, because I have 3 G's to the left and 4 G's to the right, every G is a valid starting point for a photo for the left, and every G on the right is a valid stopping point for a photo. So what that means is that I've got a photo for example, from this G standpoint, I can go up to the first G, I can go up to the second G, I can go up to the third G, and I can go up to the fourth G. Same applies for this G. For this G, I can go to the first. Let me switch to a blank screen here. I can go to the first, I can go to the second, I can go to the third, and I can go to the fourth. For this G here, I can go starting to look like music notes. First one, second one, third one, and fourth one. Okay, so each of these has 4 ending spots. So that's just 3 times 4. And we don't actually even need to calculate that by looking through everyone, because we know that we've only got one H, because we started at an H, and we went until we found another H and stopped, which means we have only G's on the left side of the subset. We have only G's on the right side of the subset. We've guaranteed that H is a lonely cow. And we know that the number of photos starting on the left and ending on the right is going to be 3 times 4. But we also have to take into account that on the left side, we have a photo here, including the H in those 2 G's and the H in those 3 G's. The number of photos you have is going to be the number of G's there are, 3 minus 1. The reason it's minus 1 is because this very first G is not a valid stopping point for a photo that has H on the right. If you want to have photos where it's just the cows to the left of H, then we can't stop at this one here, but we can stop at the second one, and we can stop at the third one. So that's 3 minus 1. And also this has to be a positive number. We'll come back to that in 1 second. Looking on the right side, same story. I've got 4 cows on the right, but this first cow isn't a valid stopping point for H on the left side of the photo. I only have 1, 2, 3, which again is 4 minus 1. Now, situations where you have to watch out for this is if I have like HG, and again, this is why you do this with paper pencils, try every possible combination you can think of. If I have HGH like that, then I've only got 1 cow on this side. Now, the first part, 1 times 4, still works. I've got 1, 2, 3, 4. But if I look at how many photos I have on the left side, I've got 1 cow. And if I do minus 1, then it shows 0 photos. If I have 0 cows and I do minus 1, then I have -1 photo. For example, if I had HH like that, HH, and then GGG, I would have 0 G's on this side. Now, the multiplication still holds up because it's 0 times 4, which is still 0. There's no photos that start on the left side of G and end on the right side of G because I have 0 cows on the left side. The number of cows on the left side, however, are not adequately reflected as 0 minus 1. If I have 1 single cow, it won't crash, it'll function. If I have 1 single G, then I'll have 1 minus 1 and it's 0. But if I have 0 of them, I have to special handle that. So what you've got then is you've got 3 parts. If I have the number of cows on the left, let me go ahead and put this back, G, 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 and H. If I have the number of cows on the left as 3, and the number of cows on the right as 4, for example, first thing I have to do is I have to add the number of cows on the left, number of cows on the left times the number of cows on the right. And again, even if there's 0 cows, that'll be fine. Next thing I have to do is I have to check to see if L is greater than 1. Because if I've only got 1 cow, then I can't have a photo with H on the right side. This is just for photos where H is going to be the right side. So if L is greater than 1, then I have to add L minus 1 to my answer. So in this case, with 3 cows, I would be adding 2. And then also, if R is greater than 1 for the same reason, then we have to add R minus 1 to our answer. All that's left to do is to run through and do that for every single cow. So what's going to happen is you're going to have an I, just probably a for loop, or if you're in Python, you'll do for I in range, whatever it is, starting here. And for every single cow, use a while loop to just count how many are on the left and count how many are on the right. So for the H, how many different are on the left? So for the H, I have 0 on the left. And then on the right here, I've got 3. First thing I would add is 0 times 3, which is just 0. Next thing I would add is if the number of G's on the left side is greater than 1, which it's not, so I don't have to add anything. And then if the number of G's on the right side is greater than 1, in that case it is, then I would add 3 minus 1, which is 2. So far with that H, I only have 2. And just to underline what those 2 are, I have this photo here, HGG, and this photo here, HGGG. Moving along, we have to do this for every cow. So for the G, I want to count how many are different on the right. There are 0 different ones on the right. There's 1 different one on the left. So I got to add 1 times 0, which is 0. If this is greater than 1, I could add, and if this is greater than 1, I could add, but neither of those are true, so I'm done. I'm going to do it for the next cow, G. I'm going to have 0 on this side, 0 on this side, so I don't have any lonely photos. 0 times 0 and 0 plus 0 is nothing. This one here has 0 on this side, 1 on this side. Both of those are not greater than 1, so I don't get to add a left side or right side photo for G because I can't do GH because there's not enough there. And likewise, there's no photos starting on the left side of that G and ending on the right side of the G because there's no H's. So once again, moving on. Reaching this H, my loop is going to run back here and discover 3 cows. It's going to run here and discover 4 cows. So I'm going to add 3 times 4, which is 12. I'm going to add 1 less than 3, which is 2. And I'm going to add 1 less than 4, which is 3, because both of those are greater than 1. And then the same process is going to happen all the way to that last cow. There's not enough here, there's not enough here, there's not enough here, there's not enough here. This H will find 4 cows on the left, 1, 2, 3, 4, and then 0 cows on the right. So 4 times 0 is 0, and there's not enough on this side to add anything, but the 4 is big enough, so I'm going to add another 3. And that is photos 1, 2, 3, and then all the ones we underlined in the beginning, which is like for every starting and every stopping point, which is the whole entire thing. HGH, GGH, G, and so forth. A whole bunch of them down there. There's 12 of them. I don't want to write them all out. So final answer, you'll have 12, 2, 2, 3, and 3, which is, what is that, 6, 8, 20, 22. I think I calculated earlier, that would be 22. So yeah, so that is the general process. So regarding the time complexity, since we're on the topic of it, and I kind of have mentioned it a couple times, the reason why this is actually in linear time is because if you think about it, it feels like it should be an n-squared algorithm, because for every cow, you're potentially having to look at every other cow. But because of the nature of the problem, because we stop when we hit something that's the same, if I happen to have a long sequence of different values from this, that means that each one of them would not have had any values that they had to seek through on the right side. So what happens then is if you look at how many times each one of these gets visited, this one, this H, is going to visit each of these G's 1 time. This G is not going to visit any of these G's because they're the same. This G is not going to visit either of those G's because they're the same. The only time those G's get visited a second time is when you get to that H. So if you think about worst case scenario, your worst case scenario is going to be essentially where you have it broken up such that you have short sequences. But even then, that's going to be pretty simple, because if I have these values, if I have 10 values here, if I have alternating GH, 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 then each one only has to look at like 2 cows on each side. If I have longer sequences like HGGG, HGGGH, then the H's have to do a little bit more work, but the G's don't have to do any work at all. So ultimately what's happening is you're really only visiting every node a linear number of times. The most number of times any given node can be visited is once from the left, once from the right, and then once when it arrives on itself. And then I guess for each of the neighbors, it'd be like an extra 2 because you have to verify that they're different. But each node can only possibly be visited 5 times. So because when I look at this from this node, I'll compare this G. From the node directly next to it, I'll compare the G. I'll compare it when I'm on the G, and from the node after it, I'll compare the G. From the H, I'll compare the G. If that gets any longer, like H, G, 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 H, then, for example, this node is only going to get visited by its immediate neighbors and by the H's. But this node right here is going to get blocked way before it gets there. So we don't have any added complexity for this. It still only gets visited 5 times. So basically, that's kind of what optimizes this problem. And then if you were to actually run through and solve this, you would have H, and then each one of these pretty much only does 2 checks. With this G here, you would check the left, check the right. That's only doing a total of 2 checks on either side before moving on. So it essentially is going to process in linear time. It just has it's an additive linear process. But this is important to note because a lot of people thought this would be an n-squared time, but because of the nature of the problem and because we can't go through a sequence of identical values if we started on that same value, that's going to prevent the number of times naturally that each node can be visited. And I think if you want to have a worst case scenario, it's like square root of n sequences. So you'd have like h. If you had like, for example, 16, then it would be like h, and then 1, 2, 3, h, 1, 2, 3. We don't really need to worry about that though. But that would be like square root 4. So you'd have like 4, 4, 4, and 4. But then even then, like each of these h's is only going to have to do square root of n work, which simplifies the process. So anyway, that's the algorithm. Just real quick to kind of recap. What you're going to do, oops, I can switch tabs here. Oops, ran out of batteries. Okay, what we're going to do is read in this number, read in your sequence. Once we've read in the sequence, once we read in the sequence, go through each node one by one. For each node, count how many are different to the left, count how many are different to the right, multiply those two numbers, then check to see if each one is greater than 1, and if so, subtract 1 from it and add that to your total, and that actually gets through the all the test cases, including the bonus 11th test case. All right, so that's how to solve the problem. Good luck coding it, and we'll talk to you on the next one.